So here we are going to go over some of the calculations and at least outline the types of equations that we should be using for these calculations. All right, so kind of like the um, field equation involves taking the Coulomb's law, F is equal to K QQ over R squared, and removing one of those charges because we're factoring out one of those charges. Um, and when we factor out one of those charges, one of the things we get is our field is equal to KQ over R squared. When it comes to the electric potential due to a point charge, all right, so we can see kind of for forces, we remove one of those charges to get to our field. For our electric potential or our voltage, we say the voltage due to a point charge is equal to K Q, right, the charge of that point charge, divided by R, the distance, any distance from that single point charge. So at every single point around one of these point charges, we should observe the same potential. Unless there's other charges in that same space, this is where you would calculate the electric potential due to this point. So what we see here is we have a coordinate system. We have in my question, it's 6.9 microcoulomb charge. Remember that a microcoulomb is 10 to the negative 6 coulombs. And in order to find the electric potential, I should be using this equation. V is equal to KQ over R, and that point is exactly 3 meters from my origin or from my charge. So if we think about a coordinate system where my charge is at the center of that point, at the center of this coordinate system, then at the point 3, 0, then I will have my location that is exactly 3 meters, right? On the other hand, if my location is at 3, negative 3, then I am going to have to use a little bit of trigonometry. I erased everything, so I'm just trying to pick back up and say that when I am calculating the electric potential, it's just the distance between the charged particle and we're finding the electric potential at a location some distance r from that. So for 3, 0, that distance is just going to be 3 meters in this case. On the other hand, if my location is 3, 3, well, I got to use just a little bit of trigonometry because I know that this is 3, this is 3. So the actual distance that I want to be using is this hypotenuse here, which would be a distance of 3 root 2. So in this case, we would have a larger distance for the point at 3, 3. But in terms of the equation, again, it would be K, Coulomb's constant, times, right, the charge, 6.9 microcoulombs for me, divided by this distance. And it's no longer squared because that is not how the equation for electric potential works. All right, so hopefully that'll help us with that question. Moving on to, all right, so on the second question, we're actually looking for electric potential energy. So when we talk about electric potential, voltage is equal to KQ over R. But what does that really tell us? The other thing that we can say, as we had before, is electric potential energy divided by the amount of charge, right? The amount of energy per unit of charge at a given location in space. If we have a charge in that location, we can calculate its energy by saying that the electric potential energy is equal to voltage multiplied by that charge. And that is what we should probably do here. Since KQ over R is our voltage, and we multiply one of those charges back, we would say electric potential energy is equal to KQQ over R squared, or sorry, over R. And actually, since these are all identical charges, that makes this really simple. And they're all the same distance away. So I can calculate the electric potential energy that one of these, that a pair of these would have between them. And then keep in mind that there's this pair, and this pair. And I would have basically 3 times the amount of electric potential energy that I would find by doing one of these calculations for the electric potential energy between two of these charges. Here we have the last question, which again is about electric potential energy. Just like gravitational potential energy, it can be converted into other forms of energy. So here, what it's really asking is about finding the electric potential energy and then converting that into a kinetic energy. So if we think again about our equation for electric potential energy is the product of our electric potential or voltage and the amount of charge we have. In this case, it's saying, well, we have a battery that maintains a electric potential of 12 volts. That means that the energy it can give us really depends on how much charge is going through those 12 volts. I could have a 50,000 volt battery, but if I don't have very much charge moving through that voltage, it still is not going to supply a lot of energy. But we have 7.5 times 10 to the 5 coulombs of charge, so that's actually a pretty significant amount. As we know, 1 coulomb is a lot. And so we want to see what the electric potential energy is simply by multiplying voltage and charge. The second question, the question is actually asking us about how fast the car can be moving. Well, basically, I just have to do like I would do for gravitational potential energy, finding the speed of something as it falls or goes down a ramp, and I can say that my electric potential energy that I start with is converted into another form of energy, in this case, kinetic energy, setting that equal to 1/2 mv squared. Here we have the electric potential and the charge. So that gives us the electric potential energy, and we have the mass of the vehicle. We should be able to get through the rest after that. I hope this was helpful. Send me an email if this is still giving you fits, and we will work our way through it.